Hello, my name is Rob Reynolds. Welcome to Math 073, where today we're going to look at our very first lesson, sets of real numbers. A couple things you need to know about roster notation and set builder notation. We're going to look at inequality notations, less than or greater than, and absolute values of numbers. The first thing you need to know is what a set is, and it's a collection of objects. It can be either numbers or names or actually even symbols. And usually when we have sets of numbers, we'll quote them in brackets, which are hard for me to draw, and I'm sure they're hard for you to draw. Practice them. So a set containing -5, 0, and 3 would look like this. And this is called roster notation. Again, we've got two things. We've got roster notation, and then we also have set builder notation, which is a little bit harder, but roster notation is what most students like the best. So sticking with set notation here, natural numbers are those numbers that are used for counting that you would, like if your little brother was 5 years old, he would naturally start counting with 1, 2, 3. It does not include the number 0. If I wanted to include 0, then I'd be talking about the sets of whole numbers, and whole numbers would look like 0, 1, 2, 3, ... And we put that in set notation. So again, natural numbers are numbers that you naturally count. Whole numbers include 0 and 1, 2, 3. So there's your set of whole numbers. For integers is defined as whole numbers and their opposites. So again, we have the 0, and here's those whole numbers, and here's their opposites. So if we wanted to start looking at Venn diagrams, we could put natural numbers. A little bit bigger set would be whole numbers, and a little bit bigger set would be the set of integers. So it's like every whole number is an integer, but not every integer is a whole number. For example, -3 is an integer, but it's not a whole number. 2 is also an integer, which is also a whole number. So everything that's a whole, and every natural number is also a whole number except for 0. So 0 is not in this set. 0 would be in this set, and that's the only difference between the natural numbers and the whole numbers. All right, so moving along, we've got zeros neither positive nor negative, and on a number line you can represent positive and negative numbers. Positive numbers being to the right, negative numbers to the left. Let's move on to set builder notation. This is read the set of x, this bar is such that, and then x is an odd number, less than. So you could write this set builder notation as roster notation by looking at all odd numbers less than 9. Well, again, they have to be natural numbers, so we can't choose like -3 because your 5-year-old brother wouldn't naturally count -3. So we're starting at 1, 3, 5, 7, and then we have to think, is 9 less than 9? And I don't think it is. And so here's your set notation for, roster notation opposed to set builder notation. Roster notation is equivalent to saying this. This is a little bit longer. A set builder notation takes a little bit more time. Looks like most students are a little bit more comfortable, including myself, with roster notation. So here's another example. Name the set containing the first 6 even, has to be whole numbers, using both roster and set. Let's start with roster. On an earlier slide, we talked about 0 being a whole number, and we also talked about 0 being neither positive nor negative. It's a neutral number, but we are not talking about positive or negative. We're talking about even and odd. So we have to make a decision whether 0 is an even number, and let's define it as even. So is 2, 4, 6, and 8. And I'm going to go for the first 6. So 1, 2, 3, 4, 5, 6. So I better go up to 10. And again, set notation, put some commas. Now, we are done with roster notation, and now we need to put into set builder notation. And set builder notation is a little bit more difficult. It still does the set symbols, but we do x such that x is an even, the first 6 even, such that x is the first 6 even whole numbers. and you write that out. I think that's done here for you. X such that X is one of the first 6 even whole numbers, and then we'd close the set notation. All right, so the advantage of a set builder notation is that it's easier for large sets, a lot easier than roster notation. Plus roster notation, you have to use a bunch of words. So if we have such that P divided by Q such that P is an integer, Q is an integer, but Q can't be equal to 0 because you can't divide by 0. That's going to be defined as a rational number. The first 5 letters of rationals spell ratio, and that's all that a rational number is a ratio. So for example, 5 is a rational number because it can be written as the ratio 5 divided by 1. And 2/3 is also a ratio because it's a fraction. So anything that's a fraction or can be written as a fraction. 0.3 is also can be written as 3/10. It's also 0.3 would be another example of a fraction. Examples that, 0.33333 repeating is also a fraction, as you may know as 1/3. Things that are not fractions would be like pi, because that's 3.1415, and that goes on 11415. Sorry, my pen's freaking out here. And later in the course, we're going to learn about E being 2.71828, and that goes on. So things that never repeat, never terminate, never stop, those are called irrational numbers, and we keep those out. So anything that terminates or repeats is going to be in the set of rational numbers. As I could write it as a ratio. So here's some ratios to put them on a number line. The easiest thing is to convert those to decimals. The square root of 10, again, cannot be written as a rational number, so we call those irrational numbers. If you type in the square root of 10, it never repeats, never terminates. The square root of 2 never repeats. It's a long stringy decimal. Pi, long stringy decimal, long stringy decimal. The square root of 13, be careful. The square root of 4 looks irrational, but you can simplify it to be a nice rational number 2. So irrational numbers are numbers whose decimals represents neither terminates nor it repeats. So again, we're going to do some Venn diagram. This is how the book kind of puts out this Venn diagram. I like the Venn diagram I'll draw it here for you. So we have rational numbers, we have irrational numbers. Irrational would be like the square root of 2 and pi and e. Rational numbers they're both real numbers. So rational numbers are real, and irrational numbers are also the real numbers. We're going to be talking about imaginary numbers also in this course, and we'll get to those later. And I just don't like the name of imaginary numbers because it sounds like we're making them up, but they have real world applications. So there's another set out here that's even bigger, and we'll talk about that. Maybe you've seen this a plus bi form. We'll talk about that later. So again, in set notations, x such that a rational number or x is an irrational. So anything that's rational or irrational is a real number. Next, we're going to look at some inequality and how to write inequality signs. This is less than. Remember, less than points to the left, and we use less than signs. So you can see all these less than symbols points to the left. So you can even see this is the less than symbol. You can write the word left and less from the less than symbol. And I like the left, put the lower number on the left. All the L rules. So greater than, -2, be careful when you're talking about negative numbers. -2 is greater than -7. If you look at a number line, -2 is further to the right of -7. So numbers over here are greater, where these numbers over here off to the left are less. So be careful. Things are opposite on the negative side. So we could try a couple examples. 4 is less than 9, so I'll go less than. -8 is less than. 7 is greater than, -21 is less than, and -2.7. Well, maybe I would even want to convert this into a decimal, -1.5, and then I could see, -2 is lower. And here are some correct answers. -2.7 is lower. You can try these. I'll give you a second Why don't you pause the video and try those. Here are some answers. Positive numbers are numbers that are greater than 0. Negative numbers are less than numbers that are less than 0. Remember, 0 is neither positive nor negative, but we're going to define it as an even number. A is always less than B, also is the meaning that B is greater than A. So we could talk about how letters could also represent numbers. So if A being any number that's less than -5, that's the same thing as saying -5 is greater than A. For example, we could come up with thinking of a number that's less than -5, like, -6 is less than -5. That's the same thing as saying -5 is greater than -6. I like the lower number on the left, but it has the same meaning. So again, we could talk about equals to, and in that way that I could look at A equaling B, here B equaling A. So the difference is if I have, like, this one is just 4 is greater than 5. So this one, it would be -2 is less than or equal to 3. Well, it's not equal to 3, but it certainly is less than. So it kind of makes more sense to use letters, because then I could represent, if A is less than or equal to 3, then I'd be talking about 3 as a possibility. Where if I just said A is less than 3, then 3 is no longer a possibility to be in a set. So again, here's a couple examples. They're saying, hey, define this whether it's true or false. I'll give you a second to try to look at these. Again, you might want to change this to a decimal. Maybe you don't have to, but if you look at these in decimal form, sometimes they're a little bit easier. Here are some answers. We should have gotten true, true, false, and true. And some replacements for the variables of inequalities make it true, and some make it false. A replacement that makes it true is called a solution. And the set of all solutions is a solution set. And then we're going to start graphing on a number line what they look like. So I might have the solution, everything off to the right. So graphing this, I want all the values of x that are greater than. So since it's not equal to, I'm going to use an open dot to represent all the values that are not equal to 3 but right next to 3. So I'll put an open dot at -3, and I want all the values that are greater than, or I'd shade everything over here. The author is not going to use an open dot and closed dot. This author is going to use a parentheses and a bracket. So if I would have said x is greater than or equal to -3, instead of putting a closed dot like you did back in Algebra 1, we're going to start using a bracket, meaning I can include the value here. An open dot means the same thing as a parentheses, meaning I cannot include. So I will not include everything up to 3. You can see that 3 is right here, and it's just bending a little bit less than. So how about -2.9? Yes, works, but -3 does not. So here we go. This one would be a bracket at 2, and I want everything that's less than, so I'm going to go this direction. Again, I can equal the value at 2, so it's a bracket instead of a parentheses. Absolute values really talk about distance from 0. So the absolute value of 6 is 6 because it's 6 units away from 0, but the absolute value of -6 is also 6 because it's also 6 units away from 0. So again, I don't care about direction, I'm just talking about distance, and that's what absolute value is, distance from 0. So we use the symbol absolute value means distance from 0. We use these 2 bars to represent absolute value of x. By the way, the definition of the absolute value of x is a little bit confusing. The absolute value of x could be positive or it could be negative, and that bothers some students because they're thinking, no, when I take the absolute value, it's always a positive number. But if I were to look at this definition a little bit more closely, I could look at this and say, well, that's true if I'm talking about numbers that are, well, here for those values of x that are greater than 0, but this is true for those values of x that are less than 0. For example, if I have the absolute value of -5, that is equal to negative negative 5 because two negatives make it back to a positive 5. So this negative right here would represent this negative this negative is what I'm talking about. Which really maybe it make more sense if I were to change the definition and call that the opposite. So this is the same, and this here would be the opposite. So it's the opposite of a negative, which makes that positive. A little bit confusing. To find the absolute value if a number is negative, the absolute value of it is the opposite, is what this definition is talking about. So again, you're right. The answers are always going to be positive. Nothing's changed. I was just trying to explain the definition of the oppositeness. So I'm going to take the opposite of negative 7 here and make it positive 7. The distance from 0 here is 12. The absolute value of 0 is 0, and you can finish these up yourself. That concludes our first lesson. I hope you found this helpful. Email me with questions.